particles. Casimir effect. So Casimir, some people go out and they try to go to high energy accelerators and look through powerful telescopes. Casimir studied his lunch. He was eating mayonnaise, and he was wondering why it flowed so slowly. So it turns out that the particles in mayonnaise have some kind of strange attraction to each other that isn't predicted classically. Extrapolated, that strange attraction allows parallel plates to attract when no classical force indicates they should. So if you take two parallel plates and you put them really close to each other, classical physics would say, oh, cool, you have two parallel plates really close to each other. But quantum effects would say, oh, no, they're going to attract. They're going to attract pretty strongly, too. Actually, I think it's a distance to the fourth effect. And the reason is virtual particles. Actually, the lack of some virtual particles, because some virtual particle modes can't survive in the cavity in the middle. And so the lack of those, on the outside you have all the virtual particle modes over here pushing and pulling, but in the middle you're missing some because they're standing waves, things drop out, interference, and you get an attraction, a strong attraction. The 0-point energy of the vacuum has changed. These plates, the classical example of two plates close together leads to an attraction, but there are ways of constructing things so that you get a repulsion as well. So the Casimir effect does not only have to be attractive. If forces result from exchanging virtual particles and the corresponding real particles always have positive mass, how can the force be attractive? This is the thing that I've wondered about for a long time. So the answer is that virtual particles can carry negative momentum, as I indicated earlier. Interference with other virtual particles can determine attractive or negative, whether you see it in attractive or negative momentum. And the calculation can get complex, but really what happens is if you have something here, you have a person here, and you have a person here and they're charged in opposite ways, then you can emit there can be a virtual particle that moves here and there, but that creates a force that goes in the other direction. Remember, these things are off the mass shell. Math is complicated. To get into the details, which I don't completely understand, you'd have to get into the guts of quantum electrodynamics. Can they go faster than light? Yes. Strangely enough, virtual particles can do lots of things. Virtual particles are a little bit like Superman or Superwoman. They can go faster than light, they can go slower than light. Those can be the terms that take them off the mass shell. However, you can't communicate faster than light. That seems to be a universal effect. No communication, FTL, faster than light is what this means. FTL, faster than light. So two well-separated observers, so we can go back to our Alice and Bob over here. This could be Alice, A, Bob, B. They could be measuring fluctuations in a field. And they would say, oh, field got a little stronger, oh, field got a little weaker. And they would each be doing that. That could be attributed to virtual particles zipping around faster than the speed of light. However, just like in versions of entangled particles, the correlations between the observers' fluctuations could only be found later. You can't predict what fluctuations you will see. Unpredictable. Because it's unpredictable, it puts a limit and you can't communicate faster than the speed of light. Strange stuff. Black hole gravity. Here's another thing I used to wonder. How is it that gravity gets out of a black hole? There's a good link under here, so you might want to click there and see discussions on the FAQ of physics, and also there's also other discussions. So first of all, general relativity doesn't really have virtual particles, so it doesn't have this problem. General relativity just has curved space. It's the curved space that causes things. So gravitons, virtual gravitons, don't have to get out of a black hole. They don't need to go there. So, but people think that general relativity isn't really the final word on gravity. They expect there is virtual gravitons around, and how do they get out of a black hole? For instance, how does a charged black hole, how does a magnetic field get out of a black hole? Well, some gravity. Another thing I didn't say is that it's possible when things fall into a black hole, and we're going to do a lot of black hole stuff later in this, because things build up around the event horizon. They fall in actually, but as far as we see them, they appear to build up there. So some of it hasn't fallen in. So that's another reason why gravity can get out of a black hole, because it's built up around the horizon. However, it is quite possible and does have an effect that virtual gravitons can come from the inside and go out. Now, the black hole can only stop. The reason why it's a black hole is because light can't escape. But if something can move faster than the speed of light, it should be able to get out. Similarly, the virtual photons of the electric and magnetic fields should be able to get out of a black hole. Now, we haven't been able to go out to a black hole and see this, but that's what we expect. However, these things cannot carry messages again faster than light. So here's a quote that I haven't been able to find attributed to any one person. It's really food for thought. All photons are virtual photons. It's a statement that gets debated in some physics boards a lot. Since photons travel at speed, they experience no passing of time between emission and absorption. That's one reason why one might consider that all photons are virtual photons. They're also treated as mathematically similar in many quantum calculations. Also, you might consider that when a photon's moving along, it's continually changing into all kinds of things. Other photons, virtual electron, positron pairs, all kinds of stuff as it goes. And only when the photon is absorbed does it really have to give up its true photonicity. So not only does an electron have a virtual photon cloud, but a real photon can be considered to be participating in this sea of strange particles that are virtual particles that are being created all the time. It's continually jumping around into many different things. And these are shown by integrals. You have to integrate over all the things it can become many times when you're doing quantum mechanical calculations. So real particles, though, can trigger real detectors, but virtual particles can only transmit force. So I'll close with a thought that I've wondered is, do virtual particles respond to gravity at all? So this, again, we don't really have data on this. I actually wrote a paper questioning whether even in our solar system this could be seen. Do virtual particles, or are they also immune? They can get out of a black hole, but what about the solar ones? Even if they're going faster than speed of light and get out of a black hole, do some of them, are they deflected by gravity in any way? Or virtual particles automatically, no matter what's around, no matter what the universe has, no matter what black holes have, they just fly straight as seen from infinity. They're always in flat space. So there are many things about physics that we don't understand, and this, I think, is something that I'd like to see better investigated in the future. And with that, I will close and ask you to keep Schrodinger away from your cat. Thanks.